Okay, in this lecture we're going to cover the section 2.3 material on the dot product. Now in our previous sections we had introduced the idea of a vector, either in the plane or in space, and we defined a few operations that we can perform on vectors, namely addition, subtraction, or scalar multiplication. So in this section we'll talk about another operation that we can perform on vectors called the dot product. So here we're going to start talking about when we can multiply two vectors, and there are different types of products we'll talk about in this chapter, and then we'll take a look at some geometric interpretation of what these products might represent. So we'll start by introducing a product called the dot product of two vectors. And it's defined as following. So let's suppose that we have two vectors A and B in space, so in 3 dimensions, whose components are A1, A2, A3, and B1, B2, B3. So we define the dot product of those two vectors as follows. So first off, the notation for the dot product is given as the vector A dot B. And it's defined as the sum of the products of these components of these two vectors. So that is, we start by taking A1 times B1. That is the product of the first components of the vectors A and B. Then we add the product A2 times B2. That is the product of the second components of those vectors. And we add A3 times B3, the product of the third components of those vectors. So the dot product is defined as the sum of the products of these components of our vectors. So let's look at an example of calculating the dot product for a couple of vectors, and then we'll start to talk about some applications of the dot product in some sort of geometric interpretation. So here we're asked to find the dot product of the given pairs of vectors, and in part A, we have the vectors A and B whose components are given here. So using this definition, the dot product A dot B is found by taking the product of the first two components, so 2 times -3, plus the product of the second components, 3 times 5, plus the product of the third components, -1 times 4. So that gives us a -6 plus 15 minus 4, which leaves us with 5 for the dot product of those two vectors. So notice that here, for the dot product, we're multiplying two vectors, and what we get back is a scalar. That is, the dot product of two vectors is a scalar, just some number. It is not a vector. Now in part B, we have vectors u and v, which are written in terms of the standard basis vectors, I, j, and k. But remember that this notation is the same as the angle bracket notation, where here u has a first component of 2, a second component of 9, and a third component of -1. So we call these the I, j, and k components of our vector. And v would have an I component of -3, j component of 1, and a k component of -4. So just two different notations for expressing these vectors. So to get the dot product of these two, u dot v, we would have the product of their first components. So here, 2 times -3, plus the product of the j components, which would be 9 times 1, plus the product of the k components, -1 and -4. So this gives us a -6 plus 9 plus 4 or 7. So again, here I want to stress the dot product of two vectors is not a vector, but it is some number. Or when we're talking about vectors, we would refer to a number as a scalar. So how can we make use of this dot product? And how might we associate the dot product with some sort of geometric interpretation for our vectors? So we can make use of the following theorem, which illustrates that the dot product is related to the angle between two vectors. So this theorem I will call the angle between vectors formula, which says if theta is the angle between two non-zero vectors A and B, then cosine of that angle theta is given by the ratio of the dot product of A and B divided by the product of the magnitudes or the lengths of A and B. Now this theorem, or the formula given in this theorem, also immediately implies that the dot product A times B of two vectors could be calculated as the magnitude of A times the magnitude of B times cosine of the angle between those vectors. So this theorem also gives us an alternative formula for the dot product. So here, two ways that we can think about defining the dot product. Either using this first definition as the sum of the products of the components of our vector, or using this new formula, the dot product can be thought of as the product of the magnitudes of our vectors times cosine of the angle between those vectors. So let's look at an example involving this angle between vectors problem, and then we'll see how we could use the dot product to determine whether the angle between our vectors might be acute, obtuse, or right. So in the first part of this problem, we're asked to find the angle between the vectors A and B. So there's three things that we need to calculate in order to use the angle between vectors formula that we had introduced in our theorem. The first is the dot product of these two vectors, A dot B, which would be calculated as the sum of the products of the components of these vectors. So multiplying our first two components, 1 and 3, we have 3, plus the product of the second two components, 2 times 4 would be 8, plus the product of the third components, 2 times 0 would be 0. So we're left with 3 plus 8, or 11. And the other two components that we need for our formula are the magnitude, or the length of the vector A, and the magnitude, or the length of this vector B. So recall, to find the magnitude of a vector, we're taking the square root of the sum of the squares of its components. So for A, we would have a 1 squared plus 2 squared, which is 4, plus 2 squared is 4. So altogether we have root 9, or 3. And for the vector B, the magnitude would be the square root of 3 squared, which is 9, plus 4 squared is 16, plus 0 squared. So this gives us root 25, or 5. So using our new theorem for the angle between vectors, if theta is the angle between these vectors, then cosine of theta is given by the dot product of A and B, which we found to be 11, divided by the product of the magnitudes of A and B. So that would be 3 times 5. So we have 11 over 15. And so to find the angle between these vectors, theta, we would take the arc cosine or cosine inverse of this 11 over 15. And this would be our angle measure in radians. Now, if we're interested in determining whether two vectors, or the angle between two vectors is acute, obtuse, or right, we can make use of the dot product alone. So one way to answer that question, let's say we're given two vectors, we want to know whether the angle between them is acute, obtuse, or right. Well, we could use this angle between the vectors formula to calculate the angle theta exactly. But if we don't have a calculator, it might be a bit difficult to evaluate this expression directly to find the angle between those vectors. So how can we make use of the dot product alone to determine whether that angle is acute, obtuse, or right? So let's think about our formula here. So if theta is the angle between the two vectors a and b, we have this formula where cosine of that angle theta is given by the dot product of a and b over the product of the magnitudes. Now we know for any two vectors, the angle between them could range anywhere from 0 up to 180 degrees or pi radians. So here, just a little visual to the side. So if we have any two vectors, A and B, the angle between them, theta, could range anywhere from 0, if they're, say, pointing in the same direction, up to maybe 180 degrees or pi radians. And if we were to go past that, so why couldn't it go past pi radians? Well, let's say that we rotated more than 180 degrees, then the angle between these vectors A and B would be defined as this shorter angle between them. So theta has to range from 0 to pi. So let's look at cosine of theta on that 0 to pi interval. So here I'm going to plot my cosine theta function as a function of theta. So we know that at 0, well, cosine of 0 would be 1, and it decreases to 0 when theta is pi over 2, and then it continues to decrease to -1 when theta is pi. So if the angle between my two vectors, theta, is acute, that is, if this angle is somewhere between 0 and pi over 2 radians, or less than 90 degrees, then cosine of theta, which is graphed here, would have to be positive. It's lying above the horizontal. Now, if cosine of theta is positive, let's look at our formula here. So cosine of theta is given by the dot product divided by the product of the magnitudes. So we know that the magnitudes, or the lengths of these two vectors, have to be positive. So the sign of cosine of theta is just determined by the dot product. So if the dot product of my two vectors is a positive number, that means that cosine of theta is positive, and the angle would be acute. So a little summary here, we would say that the angle is acute if, really if and only if, the dot product of A and B is positive. Now we would say the angle between two vectors is obtuse if theta, the angle between them, lies between pi over 2 and pi radians, or between 90 degrees and 180 degrees, which means that cosine of theta, the graph shown here, would be negative, and so the dot product of A and B would have to be negative. So we could say that our angle is obtuse if and only if the dot product of A and B is negative. So the only other question is, well, when would these two vectors form a 90-degree angle? Well, exactly when the angle between them is 90 degrees, or pi over 2 radians, which would mean that cosine of theta has to equal 0, or the dot product of A and B would have to be 0. So the dot product alone, in particular the sign of the dot product, can be used to determine whether the angle between two vectors is acute, obtuse, or right. So in this first example that we had considered, we found the dot product of A and B was 11, which is positive. So the angle between these two vectors is an acute angle. So even though we don't know exactly what arc cosine of 11 over 15 is, it is some value between 0 and pi over 2 radians. So now that we've discussed determining the angle between these vectors, let's introduce a little more terminology and see some other applications of this dot product. So we would say geometrically that two non-zero vectors, A and B, are parallel to one another if there exists a non-zero scalar C such that one vector A is a scalar multiple of B. That is, if A is equal to C times B. And that sort of makes sense. Let's think about parallel vectors. So two vectors A and B are called parallel to one another if maybe they point in the exact same direction and one is just a little bit longer or shorter than the other, which would mean that one is a scalar multiple of the other. Or maybe they would be parallel if they have different lengths, but maybe they're pointing in the exact opposite direction of one another. But in either case, we see that this vector A or the vector B is some scalar multiple of A. So two vectors are parallel if they are non-zero scalar multiples of one another. Now we would say also that two vectors are orthogonal or perpendicular if the angle between them is theta equals pi over 2 radians. So a little new terminology here. When we're talking about vectors, we would say that two vectors are perpendicular or orthogonal. So orthogonal is sort of a fancy math term for perpendicular, which we'll be using throughout the course. So just a heads up there, when you see orthogonal, that really means perpendicular. So two vectors are orthogonal if they form a right angle, which means that the angle between them is pi over 2 radians or 90 degrees. Now, some convention that we give here is that the zero vector, so that is the vector whose components are all 0, is considered to be orthogonal to all vectors because it's the only vector that doesn't have any direction. So technically, we will use the convention that it is orthogonal to every vector since it has no direction. We would say it forms a 90-degree angle with any vector. So how can we determine whether two vectors are orthogonal using the dot product? Well, we have a result here known as the orthogonal vector theorem, which says that two vectors A and B are orthogonal to one another if and only if their dot product is 0. And we've already seen that in our discussion just before this definition. So we know two vectors are orthogonal or perpendicular to one another if the angle between them, theta, is 90 degrees or pi over 2 radians. And we saw that the dot product of two vectors was given by the product of the magnitudes of A and B times cosine of the angle between them. So if the angle between them is pi over 2 radians, well, we have the magnitude of A times the magnitude of B times cosine of pi over 2, which is 0. So the dot product would have to be 0 in order for two vectors to be orthogonal to one another. So let's take a look at some examples. So here we're given the problem of determining whether a given pair of vectors is orthogonal, parallel, or neither. And in part A, we have the vectors A and B given here. So the first thing I'll test is whether these two vectors are orthogonal. So the test for orthogonality is whether the dot product of these two vectors is 0. So let's start by calculating the dot product. A dot B would be given by 3 plus 5 plus the product of the last two components, which is negative 8. So our dot product is 8 minus 8, which is 0. So if the dot product is 0, we can say that A and B are orthogonal. So here these two vectors are orthogonal to one another. They form a 90-degree angle. Now in part B, we're given two other vectors, A and B. So let's test first off whether they are orthogonal by looking at our dot product. So A dot B would be given by a negative 8 minus 2 minus 18. So we have a negative 28, which is non-zero, which means that these two vectors are not orthogonal. Now what we can say here is since this dot product was negative, that means that these two vectors form an angle, or the angle between these two vectors is an obtuse angle. But they are not orthogonal. So here to the side, we know they are not orthogonal since our dot product is non-zero. Now to determine whether they are parallel, we need to see whether one vector is a non-zero scalar multiple of the other. So typically a good way to see this is by comparing, starting with the first two components of my vectors. So in this case, I would be looking at 2 and negative 4. And I asked myself, well, how would I get from this first component of one vector to the other? So to get from 2 to a negative 4, I would have to multiply that first component by negative 2. So let's then ask ourselves whether all of the other components of these vectors satisfy that same scalar multiple relationship. So for instance, looking at my second components, looking at negative 1, if I multiply by negative 2, I would indeed have positive 2. And if I compare the third components, looking at 3, if I multiply by negative 2, I would have a negative 6. So here we can see, since the vector B is equal to negative 2 times the vector A, that means that these two vectors A and B are parallel. In particular, B is twice the length of A, and it points in the exact opposite direction of the vector A. So these guys are parallel since one is a non-zero scalar multiple of the other. So in part C, we're given another two vectors. Let's start by asking whether they are orthogonal by computing their dot product. So here A dot B would be given by 2 plus the product of the second components is 0, plus the product of the third components would be -6. So 2 minus 6 is -4, which is non-zero. So that means that these vectors are not orthogonal. Now the next question is whether they might be parallel. So as we did in part B, let's see whether one vector is a non-zero scalar multiple of the other. So by looking at the first two components, or the first components of these two vectors, I see that to get from 1 to 2, I would have to multiply the vector A by 2. So let's see whether that holds for all other components. So looking at my second component of A, which is 0, if I multiply by 2, I would get 0, which is not equal to the second component of B. So here we can say, since there is no scalar C such that A is equal to a constant multiple of B, A and B are not parallel. So since they were not orthogonal and not parallel, our answer here would be that they are neither. So let's look at one other example. In this next one, a common type of problem we might have is to determine all values of x such that a vector A, whose components are of the form x, x, -1, and B, whose components are 1, x, 6, are orthogonal to one another. So we know the only way that two vectors are orthogonal is if their dot product, A dot B, is equal to 0. So let's calculate our dot product here. Multiplying the first two components of A and B, we would have x, plus multiplying the second components, we would have an x squared. And then multiplying the third components, we have a -6. And this dot product would have to be 0 for these to be orthogonal. So we want to solve for x. So I first might just rearrange the order of these terms as x squared plus x minus 6 is 0. Which can then be factored as x plus 3 times x minus 2 is 0. So we find that x could be equal to -3 or +2. So two choices for x here that would make vectors of the indicated form orthogonal to one another. Now, the next thing that we're going to talk about in this section is the concept of a vector projection of one vector onto another. These vector projections have some nice applications, some of which we'll start talking about in this section. So let's start by defining the vector projection of one onto the other, or the scalar projection of one vector onto another. So we'll start here with the following definition. The vector projection of a vector A onto a vector B is the vector which is denoted as follows. So we would have PROJ, or projection, of the vector A, and then in the subscript we would say onto the vector B. And it is the vector which is defined as the dot product of A and B over the magnitude of B squared times the vector b. And we would define the scalar projection, or sometimes called the component of a vector A onto a vector B, as the scalar denoted as component of A onto B. So B is the vector in the subscript. And it's defined as the dot product of A and B divided by the magnitude of B. So let's think about where these definitions, or where the formula for these definitions comes from, and a geometric interpretation of these vector or scalar projections. So let's say that we have two vectors, maybe a vector A, and we have some other vector B. And I'm going to draw their representations such that they have the same initial point. So when I'm thinking about a vector projection of A onto B, what I mean by that is if I were to take a line extending from the terminal point of A and dropping vertically onto the vector B such that this forms a right angle, the vector projection of A onto B is going to be the vector which has the same initial point as A and B, and whose terminal point is where that vertical line is intersecting my vector B. So this is what we would call the projection of the vector A onto the vector B. So the component of this scalar projection is the magnitude of this vector projection of A onto B. So if I take the length of that vector, that's what I'm defining as the component of A onto B. It's the length along this vector. So let's see if we can justify these formulas, which we've given for the vector and the scalar projection of A onto B. So let's suppose that the angle between these two vectors is theta. So if I'm interested in finding an expression for this vector or scalar projection, let's start by looking at cosine of theta. So when we think about this triangle formed by projecting one vector down onto the other, we see it's a right triangle where one of our interior angles is theta, and we're interested in calculating the length along that adjacent edge of the triangle formed by that angle theta. So we're going to look at cosine of theta to involve that adjacent edge. So cosine of theta is going to be given by the ratio of the length of this adjacent side, which is what we're interested in, the component of A onto the vector B. And then we would divide by the length of the hypotenuse of this triangle, which would be the magnitude or length of that vector A. So we can multiply both sides of this equation by the magnitude of A, and we would have the component of A onto B as the magnitude of A times cosine of the angle between those vectors. However, cosine of the angle between those vectors is given by the dot product of those two vectors, A and B, divided by the product of their magnitudes. That was a theorem that we had a little earlier in this section. So we can see that this magnitude of A term in the numerator and denominator will cancel. And so the component of A onto B is given by the dot product of A and B divided by the magnitude of B. That was the formula that we had given in the definition. So once we have that magnitude, how can we get the vector projection of A onto B? Well, let's think about it. To get the vector projection of A onto B, I could think about taking a unit vector, that is a vector of length 1, let me call it U here, which points in the same direction as B. So that would be the vector given by, let me clean this up a little bit. So here my vector U, a unit vector in the same direction of B, could be found by taking B and dividing by its magnitude, as we did in earlier sections. And then I would scale the length of that unit vector to have the length defined by the component of A onto B. So I'm going to take the desired length of my vector, which was the component of A onto B, given by the dot product of A and B over the magnitude of B. And I'm going to multiply by a unit vector in the direction of B, which could be found by taking B and dividing by its magnitude. So what I'm left with is the dot product of A and B, and then in my denominator I had the magnitude of B times the magnitude of B, so dividing by the magnitude of B squared, and then we're taking that scalar and multiplying by this vector B. So that gives us the formula for this projection that we saw in the definition. So a little justification for those formulas and the way that these vector or scalar projections are defined. So let's look at an example of this. In our next problem, we're asked to find the vector and scalar projections of the given vector A onto the given vector B. So there's a few things that we need to calculate in order to compute these. The first of which is the dot product of A and B. So in this case, we would have the product of the first components is 4, plus the product of the second components would be -6, plus the product of the third components is -5. So we're left with a -7, which means that the angle between the vectors A and B is obtuse. Now we also have to calculate the magnitude of this vector B, which is given by the square root of the sum of the squares of its components. So here 2 squared, or 4, plus -2 squared is 4, plus -1 squared would be 1. So we're left with root 9, or 3, for the magnitude of that vector. So once we have these expressions, we're ready to calculate the component of A onto B, or the scalar projection of A onto B, which is defined as the dot product of those vectors, so -7, divided by the magnitude of B squared. Divided by just the magnitude of B. So in this case, 3. And the vector projection of A onto the vector B is calculated as the component of A onto B, that is -7/3, times a unit vector in the direction of B, that is B over the magnitude of B. So we have -7/3 times the vector, B divided by magnitude of B would give us a first component of 2 dividing by the magnitude, which was 3, a negative 2 dividing by the magnitude of B, which was 3, and our third component was negative 1. We're dividing through by its magnitude, which was 3. So for our vector projection of A onto B, we are given the vector negative 14 over 9, positive 14 over 9, and positive 7 over 9. So let's think about this particular example geometrically. What might be a little odd here, you'll notice that the projection of A onto B, looking at the sign of these first components, well, this projection of A onto B is a vector that is acting in the opposite direction of B. So what exactly does that mean here? So we had found, by looking at the dot product of A and B, since we had a negative value for that dot product, the angle between the vectors A and B is obtuse. It's greater than 90 degrees. So how would we interpret the vector projection in this case? So in this case, we could think about the line defined by the vector B, and we would be looking at projecting the vector A onto that line determined by the vector B. So here our vector projection of A onto B would be a vector acting in the opposite direction of B, and the length of that vector is our component of A onto B. So in the event that the angle between these vectors is obtuse, that means that we would be projecting A onto the line determined by that vector B, but it might be acting in a direction opposite of B. Now in the last part of this section, we'll talk about some applications of the dot product in physics or engineering. In particular, we'll see how the dot product of two vectors can be used to determine the work done by a force in moving an object along some line. So let's start with a little review of some basic physics. So let's recall that the work done by a constant force, let's say capital F, in moving an object a distance of d units is given by the product of force times distance. However, one restriction on this formula is that it only applies when the force is acting in the direction of motion. So that is if we're applying the force in the exact same direction in which our object is moving. But in several examples, that may not always be the case. So let's consider the following problem. Suppose that we have a constant force given by a vector, capital F, and it's acting on an object which is moving from a point P to a point Q, but maybe the force isn't acting in the exact direction of motion. So here we have some force vector. It's representation shown here. And this force is acting on an object which is moving from a point P to a point Q. So its representation shown here. And this vector is what we will call capital D. It is the vector from point P to point Q. And let's say that the angle between those vectors is given by theta. So if we're interested in determining the work done by that force F in moving an object along this displacement vector, d, from point P to point Q. Let's think about how we could find it. So here I mention that this work done in moving an object from P to Q depends on two things. First off, the total distance that this object has moved, which would be the magnitude or the length of our displacement vector. So that is the magnitude of the vector from point P to point Q, the total distance that our object has traveled. And the second thing that this depends on is the magnitude of the force applied in the direction of motion. So we're trying to determine the component of our force F acting in the direction of this displacement vector. So that would be the component of F onto D. So here, the length along that vector is the component. So let's think about how to find this. So the length of my vector shown in red here would be associated with cosine of the angle between those vectors, which would be given by the length of this red vector, which is the component of the force vector onto the displacement vector, divided by the magnitude of the force vector F. So solving for that component of F onto D, the same as we did in our previous discussion, we would have the magnitude of this force vector times cosine of the angle between them would be the component of the force acting in the direction of motion. So this magnitude of F times cosine of theta would be the component of our force acting in the direction of motion. So then the work done by that force F in moving the object along this displacement vector is given by W, and we would take the distance that our object has moved, that is the length of the displacement vector D, times the magnitude of the force acting in the direction of motion, which we just found to be the magnitude of F times cosine of theta. But recall that this is exactly the dot product of those two vectors F and D. Earlier in this section, when we had looked at the formula for the angle between vectors, we saw an alternative definition of the dot product of two vectors would be the product of their magnitudes times cosine of the angle between them. So in other words, the work done by some force in moving an object along some displacement vector would be the dot product of that force vector with the displacement vector. So let's look at some examples of this. In this next example, we have a force is given by the vector F, whose components are 3, 4, 5, and it's moving a particle from the point P to the point Q, and we want to find the work done. So we have already our force vector. What we still need to find is the displacement vector. So let me start by saying the displacement vector is denoted as D, and it would be the vector from the point P to the point Q. So we know how to find the components of such a vector. We would take the difference in the x-coordinates for my terminal and initial point. So we would have a 4 minus 2. For the second component, we would take the difference in the y-coordinates for my terminal and initial point, 6 minus 1. And for the third component, we would have the difference in our z-coordinates. So here, our displacement vector is the vector 2, 5, 2. So now that we have our force vector and our displacement vector, the work done by the force in moving the object along that displacement vector is the dot product of these two vectors. So multiplying their first components, we have 3 times 2 is 6, plus the product of the second components, 4 times 5 is 20, plus the product of the third components, 5 and 2 would be 10, so altogether 36. Now here we weren't given any specific unit for the magnitude of the force or the distance traveled, so this might be something like Newton meters, could be joules, so just depending on what the units are for the problem, we might have a different unit for work. So let's look at some other examples, maybe a little bit more applied. So in this next one, we're told that a woman exerts a horizontal force of 30 pounds on a crate as she pushes it up a ramp, which is 5 feet long and inclined at an angle of 20 degrees above the horizontal. And we're told to find the work done. So let's start by sketching a little diagram to illustrate what's happening here. So we're told that a woman is exerting a horizontal force on some crate. So let's say that we have a crate, and this woman is exerting a horizontal force, which I'm going to denote as F, on this crate, and it's being pushed up a ramp which is 5 feet long. So here I have some ramp. Its total length is 5 feet, and we're told that it's inclined at an angle of 20 degrees above that horizontal. So this ramp, which 5-foot ramp, which our object is moving along, will be our displacement vector. So in order to calculate the work done, we need to find the dot product of the force and this displacement vector, which can be calculated as the product of the magnitudes of these two vectors times cosine of the angle between them. And this information we're given in the problem. The magnitude of the force was 30 pounds. The displacement vector, which was our ramp, had a length of 5, so the magnitude of that vector would be 5 feet. And then we are multiplying by cosine of the angle between those vectors, which was 20 degrees. So here we have 150 times cosine of 20 degrees measured in foot-pounds, or making use of a calculator to approximate cosine of 20 degrees, we're left with 141 foot-pounds. So this example illustrating if we know the magnitude of the force, the total distance traveled by our object, and we happen to know the angle between that displacement vector and the magnitude of the force, then we can find the work done. So let's look at another example. Here we're told a boat is sailing south with the help of a wind blowing in the direction 36 degrees east of south with a magnitude of 300 pounds. And we're told to find the work done by the wind as this boat is moving a total of 150 feet. So again, let's try to sketch a little diagram here to illustrate this. So we have a boat which is traveling south. We were told a total distance of 150 feet. So this is going to be our displacement vector as the boat travels from its starting point 150 feet south. And we were told that we had a wind that was blowing in the direction 36 degrees east of south So from this southern direction, we'll rotate 36 degrees to the east. And we have this wind velocity vector, which is imparting some force on our boat. So we need to find the work done by the wind in moving the boat along this displacement vector, which would be given by the dot product of the force and the displacement vectors, which is given by the product of their magnitudes times cosine of the angle between those vectors. And all of this information we're given in the problem statement. The magnitude of the force vector, we were told, was 300 pounds. The displacement vector had a length of 150 feet. And then we're multiplying by cosine of the angle between them, which was 36 degrees. So making use of a calculator to approximate cosine of 36 degrees, we get approximately 36,406 foot-pounds. So in this section, we've defined another operation we can perform on two vectors, known as the dot product of those two vectors. And the dot product of two vectors we saw is a scalar, which can be used to calculate the work done by a force in moving an object along some distance. And it can also give us information about the angle between two vectors, in particular, whether those two vectors are orthogonal.